Hello and welcome to problem set number 12. Our topic today is solutions, concentration, and osmosis. Before we get started, I do want to remind you that the worksheet I'll be covering in this problem set video is available online through my website. And with that said, let's go ahead and get started. Number 1. How many moles of sodium sulfate are in 1 liter of a 2.50 molar solution? So remember that 2.50 molar solution, and this is sodium sulfate, so I'll go ahead and label it in a 2SO4. That this means 2.50 moles of solute, sodium sulfate in this case, per 1 liter of total solution. So if we're wondering how many moles are in 1 liter of solution, then it's just the 2.50 moles. Okay. So the answer is 2.50 moles of sodium sulfate. Because molarity means the number of moles in 1 liter of solution. Number 2, how many grams of sodium sulfate are in 1 liter of a 2.50 molar solution? Okay, so this time we're figuring out the number of grams. So again, 2.50 molar sodium sulfate means 2.50 moles of solute. Sodium sulfate is a solute in 1 liter of total solution. Okay. So we know how many moles, but we want to find out for this problem, we want to find out how many grams. Okay, so we already know that in 1 liter there's 2.50 moles of sodium sulfate. Hopefully you remember a special conversion factor that we learned about to convert between grams of a substance and moles of a substance. It's called molar mass, and we get it from the periodic table. So I'm going to go ahead and open up a periodic table here, and I'm going to look up the molar mass for sodium sulfate. So sodium is 22.99 grams per mole, and there are 2 of them. So 2 times the 22.99 grams per mole for my 2 sodiums, 2 moles of sodiums. There's 1 mole of sulfur, so I'm going to look that up here. Sulfur is 32.07 grams per mole. And my oxygen, I have 4 of them, and each one is 16. So 4 times 16.00 grams per mole. Okay, got to add all those up, and I will have my molar mass for sodium sulfate. Grab your calculator, unless you're really good at doing this in your head, plus the 32.07 plus, okay, I get 142.05 grams of sodium sulfate per mole of sodium sulfate. So I need to set this up so that my moles will cancel. So I'm going to put the 1 mole on the bottom, but my grams will not. So I'm going to put my grams on the top. The stoichiometry lesson from several tutorials ago is coming back to haunt you here. Okay, that's probably one of the hardest things about chemistry, is that everything builds. All the topics build on each other, so you really can't forget anything. All right, so I'm doing my 2.50 times 142.05. I get 355.125 grams. I'm going to go ahead and round that off to 355 grams of sodium sulfate. Okay. All right, going on to number 3. Number 3, how many moles of barium chloride are in 2.8 liters of a 1.25 molar solution? Okay, so a 1.25 molar solution of barium chloride. Make sure that you're getting this formula right, okay? And we know that this means 1.25 moles of solute, the solute is the barium chloride, per 1 liter of total solution. But in this problem, we're not talking about 1 liter of that solution. We're talking about 2.8 liters. So we need to multiply the 2.8 liters of solution through. Liters will cancel, and that will tell us how many moles are not in 1 liter, but how many moles are in the 2.8 liters. So 2.8 times 1.25, we've got 3.5 moles of barium chloride in 2.8 liters of solution. Okay. All right, number 4. How many grams of barium chloride are in 2.8 liters of a 1.25 molar solution? Okay, so again, 1.25 molar barium chloride solution. Right away, you should be thinking 1.25 moles of barium chloride per 1 liter of total solution. But just like the problem above, we're not talking about 1 liter solution, we're talking about 2.8 liters of solution. So although molarity is always out of 1, we're not talking about just 1 liter, we've got more than that. Okay, so we already did that problem. So we know that we're talking about 3.5 moles of barium chloride. We actually got that answer from above. Now we want to convert that into grams. How many grams? Not how many moles of barium chloride, but how many grams of barium chloride is that? We're going to need the molar mass. Okay, so go to your periodic table. Barium is 137.33. And each chloride is 35.45, but there are 2 of them. So 2 times 35.45 grams per mole. Add it all together. I'm going to use a calculator. It's way, way faster for me that way. Okay, I get, whoops, 70.9 plus 137.3. Okay, I get 208.23 grams per mole. Okay, so I'm going to plug that in up here. Moles on the bottom, because I want that to cancel. Grams on the top, so that's the 208.23 grams of barium chloride. And again, this is just the molar mass of barium chloride, the conversion factor that we use to convert between grams of a substance and moles of that same substance. So I'm going to multiply by the 3.5, and I get 728.805 grams of barium chloride. And I'm going to go ahead and round that off to 730 grams of barium chloride, okay, or 7.3 times 10 to the 2, if you want exponential notation. Okay. All right. So we're running out of room here. Let's erase before we go on to number 5. All right, number 5. Which of the following would you expect to be soluble in water? A, hexane, and the formula CH3, CH2, 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 CH3 is given. or methanol. And the formula CH3OH is given. Okay, so soluble in water. We know that water is a polar molecule with a partial negative charge buildup on the oxygen, partial positive charge buildup on the hydrogens. Okay, so it's capable of dipole-dipole forces of attraction. In fact, it's capable of that special type of dipolar force of attraction known as the hydrogen bond, because we have a hydrogen here that's covalently bound to oxygen, so it can strongly attract the oxygen, nitrogen, or fluorine of another molecule. Okay, and remember, like dissolves like. So we're looking for another polar substance, another molecule that's capable of dipolar forces of attraction. So in hexane, we have all carbon-carbon and carbon-hydrogen bonds. We have all nonpolar bonds. Hexane is a nonpolar molecule. In methanol, however, we have an OH bond. So we have a polar molecule that's not only capable of dipolar forces of attraction, but that is capable of those special type of dipolar forces of attraction, hydrogen bonds. So we would expect methanol, the polar methanol molecules, to be able to hydrogen bond and therefore dissolve into water, whereas our nonpolar molecule would not. So the answer here is B. Like dissolves like. Polar solutes will dissolve into polar solvents. Nonpolar will dissolve in other nonpolar solvents. All right, number 6. Normal saline is used in intravenous drips and has a concentration of 0.90% mass volume sodium chloride. Answer the following questions about preparing a solution of normal saline. A. How many grams of sodium chloride are needed to prepare 100 milliliters of normal saline? Okay, so we know that the concentration, which is given, 0.90% mass volume sodium chloride, we know that this means 0.90 grams of solute. Sodium chloride is a solute. It's a percent, so percents are always out of 100, and it's a volume, so it's 100 milliliters of total solution. So how many grams of sodium chloride are needed to make 100 milliliters of solution? Well, it would just be the 0.90 grams of sodium chloride if you're just trying to make 100 milliliters of solution. B. How many grams of sodium chloride are needed to prepare 150 milliliters of normal saline? So in this case, we're not trying to make just the 100 milliliters of solution. So we want to multiply that 150 milliliters through to figure out how many grams of solute are needed. And if you set it up with dimensional analysis, the milliliters of solution will cancel, telling you how many grams of the sodium chloride are needed. So 150 times the 0.90. So you need 135. Oops, I forgot to divide by 100, sorry. Don't forget to divide by 100. I'm going to say that doesn't really make much sense. You need 1.35 grams of sodium chloride if you want to make 150 milliliters of that solution, not just 100 milliliters, 150. Okay, let's go ahead and erase here and go on to number 7. Okay, number 7. Which of the following solutions has a higher osmolarity? A, 0.25 molar potassium chloride or 0.25 molar potassium sulfate. Okay, and I purposely wrote these out instead of giving you the formulas because I'm hoping that you tried these problems before you watch this video, and hopefully you were able to convert the name potassium chloride into this 1-to-1 ratio of cations to anions, and the name potassium sulfate into this 2-to-1 ratio of potassium cations to sulfate anions. It's very important that you're able to do that for this problem so that you can figure out the osmolarity, which tells you the number of moles of dissolved particles in 1 liter of solution. So we are given the molarity, not the osmolarity, and we want to know which one has the higher osmolarity. So remember, osmolarity is the number of dissolved particles, and ionic compounds will dissociate. They will separate in solution. So for every 1 mole of potassium chloride, you're actually going to get 2 moles of dissolved particles. 1 mole of the cations, 1 mole of the anions. So the osmolarity of a potassium chloride solution is going to be double the molarity. So it's going to be a 0.50 osmol solution. Over here, we have 2 potassium cations in 1 mole of potassium sulfate, 2 moles of potassium cations, and 1 mole of sulfate anions. So we get 1, 2, 3 dissolved particles. For every 1 mole of potassium sulfate that dissolves, we get 3 moles of dissolved particles in that solution. So the osmolarity will be triple that of the molarity. So this is going to be a 0.75 osmolar solution. So we were looking for which one has the higher osmolarity. It is going to be the 0.25 molar potassium sulfate solution. Its osmolarity is going to be 0.75 osmol. All right, part B. Now we're looking at 0.30 molar sodium chloride, okay, NaCl, or 0.30% mass volume sodium chloride. Okay, so I threw in a little bit more tricky problem here. So although it's pretty easy for us to convert the molarity into osmolarity, all we have to do is look at how many dissolved particles are freed up from this ionic compound. And we know that for every 1 mole of sodium chloride that dissolves, we're going to get a mole of sodium cations and a mole of chloride anions. So the osmolarity is just going to be double the molarity, 0.60 osmol. We can't do the same when it's in percent. So we are going to first have to convert this concentration given in mass volume percent into molarity. So let's work on that first. So we've got 0.30 grams of sodium chloride per every 100 milliliters of solution. We need to convert grams into moles and milliliters into liters so that we will have moles per liter, molarity. Okay, so we need, let's first do the easy part. Let's convert milliliters into liters. So 1,000 milliliters to 1 liter. Okay. Go ahead and write my answer down here. What are we doing? We're dividing by 100 times by 1,000, so it's going to be times by 10, 3.0 grams of NaCl per 0.1 liter of solution. Okay, and now let's go ahead and convert grams into moles. Okay, so we need the molar mass. Let's go to our periodic table. Sodium is 22.99. I'll write it here, 22.99 grams per mole. And my chloride is 35.45. Okay, add them together. I get 58.44 grams per mole for my molar mass of sodium chloride. So let's go ahead and plug that in over here. The grams goes on the bottom. The mole goes on the top. We don't want that to cancel. We want the grams to cancel. Then we're going to have moles per liter. So I'm running out of room over here. Sorry about that. So and then, all right, so my answer is, I'll write it all the way down here, 0.051 molar. All right, moles per liter. Moles of sodium chloride per 1 liter of solution. Okay, so going back up here, to figure out the osmolarity, so it's going to be double. So we've got 0.051 molar NaCl, and that's going to be double. So the osmolarity is going to be 0.102 osmol. All right, so we're comparing the 0.102 osmol to the 0.60 osmol. So now we can see that it's the 0.30 molar solution that is going to have the higher osmolarity. Okay, let's go ahead and erase all this work. That was a lot of work. And go on to number 8. Okay, number 8. Assume red blood cells are placed in an aqueous solution of 0.25 molar sodium chloride. Which of the following correctly describes the direction of water flow? So this is a question on osmosis. So let's go ahead and draw a picture here. Our red blood cells, you might remember from the tutorial, number 12, that they are 0.30 osmol. And they're placed in a solution that is 0.25 molar sodium chloride. So we first need to figure out what the osmolarity of this surrounding solution is. If it is isotonic, that is, if it is the same as the osmolarity of the red blood cells, then we would expect no net flow either into or out of the red blood cells. If the solution is hypotonic, that is, if our surrounding solution has a lower concentration, then we would expect a net flow of solvent into the red blood cells and a swelling. If our surrounding solution is hypertonic, that is, it has a greater osmolarity than the red blood cells, then we would expect a net flow of solvent out of the red blood cells, and we would expect those red blood cells to shrivel. So let's figure out what the osmolarity is here. We know for sodium chloride that we're going to get, for every 1 mole of sodium chloride, we're going to get a mole of sodium cations and a mole of chloride anions. So we're going to double the molarity value to get the osmolarity. So it's going to be 0.50 osmol. So it is a hypertonic solution, meaning that we're going to have a net flow of solvent out of the red blood cell. There will be solvent moving in as well, but there will be more solvent moving out. Remember that the solvent will always flow from the region of lower solute concentration to the region of higher solute concentration. And the higher solute concentration is outside of the red blood cells. So the best description, let's see, water will have a net flow into the red blood cells. That's not what's going to happen, so let's keep track here. A is not correct. B says water will have a net flow out of the red blood cells. B is correct. Circle B. Let's go ahead and look at C just to make sure. C says water will flow in and out of the red blood cells at equal rates. That would happen if they were isotonic. They are not, so it is not C. The answer to number 8 is B. All right, let's erase here and go on to number 9. How many milliliters of a 1.0 molar sodium hydroxide solution should be used to prepare 500 milliliters of a 0.15 molar sodium hydroxide solution? So we're talking about a dilution. Anytime you see a more concentrated solution being diluted into a less concentrated solution, you should think of the equation C1V1 equals C2V2, the dilution equation. Okay, so let's take a look at the information we're given. We've got 1.0 molar sodium hydroxide, and we're trying to use that to prepare 500 milliliters of a 0.15 molar sodium hydroxide solution. Okay. All right, so let's label C1, V1, C2, and V2 as needed. Okay, so here is our more concentrated solution, our initial solution that we're going to be diluting. Here is our desired volume of our new diluted solution. So this is V2. And here is the concentration of our desired solution. So that is C2, the concentration of our diluted solution. So what we're solving for is what volume of that more concentrated solution do we need for this dilution. So rearrange this equation and solve for V1 by dividing both sides by C1. We get V1 equals C2V2 over C1. Now plug in and solve for V1. So C2 over here, 0.15 molar. V2 is the 500 milliliters. And the concentration we're starting from is the 1.0 molar solution. Molarity is going to cancel out, leaving us in units of milliliters. That is good because we're trying to solve for the number of milliliters, the volume of solution needed. So 0.15 times the 500 divided by 1, we don't have to do. Okay. So we need 75 milliliters of that more concentrated solution. So that means that we need to measure out 75 milliliters of our 1.0 molar sodium hydroxide solution and then dilute it by adding solvent, water, up to the 500 milliliter mark. All right. Number 10. I think we can squeak it in right down here. So let's finish off with number 10. Assume you need to add 0.055 moles of hydrochloric acid to a reaction. How many milliliters of a 1.55 molar hydrochloric acid solution should you use? So we have 1.55 molar HCl. Okay. And we need to add 0.055 moles of HCl to our solution. So let's first think about what this concentration means. This means that there are 1.55 moles of solute, the HCl, in every 1 liter of total solution. Okay. So if we added an entire liter of that solution to our reaction, we'd be adding 1.55 moles of HCl. We don't want 1.55 moles. We want just 0.055 moles. So we're going to use this as a conversion factor to figure out what volume to use to get just 0.055 moles of that solute. All right, so let's set it up here. 0.055 moles of HCl. That was the right number, right? Yes, okay. In 1 liter, we're going to flip it so we get moles on the bottom of that solution. There are 1.55 moles of HCl. So the answer to this problem is going to tell us what volume in liters is needed to measure out just 0.055 moles. Okay, so we get, I'll write the answer down here, 0.035. We get a bunch more numbers, but I'm going to go ahead and round to 0.035 liters of solution. And I believe you were asked, let's see, how many milliliters. Okay, so we've got it in liters. Let's go ahead and convert that into milliliters. 0.035 liters. And in every 1 liter, there are 1,000 milliliters. So you can't even forget the metric system. Everything you learn in a chemistry class comes back to you. You have to use it again and again and again. And that's going to be the case for your whole 1 year of general chemistry. And it's also going to be the case when you get to your higher division, higher level chemistry courses as well. You cannot forget anything in chemistry class. You're going to reuse everything. All right, so we're just timing it by 1,000, so it'll be 1, 2, 3, 35 milliliters of that solution. Okay, so how much should we add to our reaction? We should add 35 milliliters of that 1.55 molar solution in order to get an addition of just 0.055 moles of HCl. All right, that is going to conclude our problem set number 12. I hope you will consider tuning in to tutorial number 13. Thank you.